Lin inflates a balloon using a helium pump. When she turns off the pump, the balloon immediately begins to deflate. Lin believes that she can model the balloon's volume in cubic feet by the function v of t is at squared over e to the bt, where t is the time in seconds after she begins inflating the balloon. And where a and b, and make sure you pay attention here a and b are parameters, which are really just some numbers. Like for all we know right now, like a could be 2 and b could be 3. And in that case, v of t would be 2t squared over e to the 3t. Or maybe a is like 2023 and b is like 0.5 for all we know. But a and b here are just some numbers that turn out to be positive, and the fact that it's positive is actually very important. I'll explain this soon enough. But the reason we care about a and b is because as a and b change, that's going to qualitatively affect the behavior of the function. So just to take maybe a simpler example, you can consider something like f of t maybe is a times t minus b squared. So this is a completely different function with parameters. Here a and b are parameter and t is the variable. And in this case, what does a and b do? Well, if you know how to graph this, you know this is a parabola where this minus b is really giving you the horizontal shift. And this a is really giving you a vertical stretch. So for example, as we vary b, your parabola, which is like opening up or maybe opening down, can be shifted left or right. So maybe when b is 1, the parabola has vertex at 1. When b is 5, the parabola is going to have vertex at 5. So as we change b, the parabola moves left and right. So that's what b is doing here qualitatively. And what does a do? What happens as we change a? Well, when a is 1, we probably have a parabola that looks like this. It's opening up like something like this, maybe when a is 1. But when we change a to, say, a equals to 2, then the parabola is going to have the same vertex, but it's going to open up a lot faster because you're vertically stretching it, say, by a factor of 2. And when a is, say, like 0.2, you're vertically compressing it, so the parabola is going to open up a lot slower. So it's going to maybe look something like this. So here, as we vary a and b, so a and b are numbers, but as we change a and b, the behavior of the function gets affected. Here, in our case, our function is obviously a lot more complicated than just a parabola, but a and b are doing something similar. In fact, what does a do here? Well, a is multiplying the entire function, so a is like a scalar in front of the function. So we know a is actually doing vertical stretch, just as it was doing vertical stretch, I guess, in the parabola example here. So as we increase a, the entire graph is going to vertically stretch up. So that's what a is doing here. But what does b do? This is a lot more mysterious, because we know, like, if it's like t minus b, we know it's a horizontal shift, but it's e raised to bt. Well, what does that do? Well, this is not as obvious as what a is doing, but as we'll find out very soon in this problem, b really affects where this maximum point, where this peak is going to be. So as we change b, the location of this maximum is going to change. Now let's read on just a little more. As an example, this function is shown to the right for one choice of the constants a and b. They're not telling us what a and b they chose. Maybe they picked 2 and 3. But for some choice of a and b, when you graph it, it looks something like this. And now we get some intuition for why this function is being used to model the volume of a balloon that Lin is inflating. Because we see, for example, from here to here, the function is going up, so that exactly corresponds to inflating the balloon. So as the balloon is inflating, the volume is increasing here. And then she turns off the pump and the balloon immediately begins to deflate. And we see the deflation happening right here. And the volume is now approaching 0 as time goes by. So this is what's really happening. And now the fact that a and b are positive constants now make a lot of sense, right? Because, for example, if a happened to be 0, then what happens? Then v of t, this entire thing just becomes 0. So you'd get a graph that looks something like this. It's always at the y-axis. And that's certainly not going to model a balloon that's inflating then deflating. So you don't want a to be 0. You probably don't want a to be negative either, because when a is negative, this is negative, t squared is always positive, exponential e to something is going to be positive, exponential to negative power is also positive. So this part is always positive. So if a was negative, then this entire thing would be negative. But volume being negative doesn't make any sense. So you don't want A being less than 0 either. Now the reason you want B to be greater than 0 may not be as obvious, but for example, if B is less than 0, think about what happens here. So for example, if B happened to be negative 1, then V of t, since you have e to the minus t in the denominator, is at squared times e to the t. I just brought this e to the minus t up to the numerator, and this you see, as t blows up, as t goes to infinity, we see V of t goes to infinity as well. Because when t gets really large, then this thing is obviously blowing up. So you're going to get a balloon that's like blowing up to size infinity, and that doesn't make any sense. Whereas if b is positive like they tell us, then when we take the limit as t goes to infinity of V of t, then below, because b is positive, you have exponential growth. Top t squared is also blowing to infinity, but this is polynomial. And if you compare polynomial versus exponential grows way faster. So even though this thing is blowing off to infinity too, what's really happening is maybe t squared is like 1000, but e to the bt is like way larger. Maybe it's like 1 quadrillion or something. So in the limit, the bottom is gonna dominate. It's approaching infinity a lot faster. So limit of V of t is actually 0. And that's what we see happening here. As time blows up, you're approaching 0, and that's probably what you want, right? Because you want the balloon to deflate towards 0, not towards infinity. So again, you don't have to really know any of this, but my point is that if A and B are not positive constants, then what you're trying to do in this real life context makes no sense. So you really want A and B to be positive. Okay, so there was a long digression, but I hope that at least got you some intuition on what's happening here. So they tell us when you differentiate V of t, so of course we can differentiate V of t ourselves using, say, quotient rule, but they did it for us. So you know V prime of t, this expression. And now let's get to the question. Part A, the function V of t appears to have a local maximum at some positive time. And yes, we see that. At least here, it looks like the maximum is happening at this time. I'm not sure what it is, but it is happening here. Find the time at which this local maximum occurs and use calculus to find your answer. And here we want to make sure we give enough evidence to show that the point we found is indeed the local maximum. So let me quickly go through what kind of techniques we can use to find local maximum. And while we're at it, let me just quickly contrast it with the techniques you need to find global maximum. So this is again bit of a digression, but I think it's good to review really quickly. So when you want to find local max or min, well, you can either use the first derivative test or the second derivative test. And to review it quickly, what does first derivative test do? Well, you first find the critical points. So maybe the critical points are like 2 and 3. I'm not sure. So these are the critical points where I guess here you're using V prime of t is either 0 or undefined. And you want to make sure you label this sign chart V prime of t if you want to get full credit. And what we do is we look at the sign in between, say maybe it's plus minus minus, and then from this you can deduce whether you have a local maximum or local minimum. Like for example here at 2, we see that you're going from V prime being positive to V prime being negative. So that corresponds to going from V of t, going from increasing to V of t, going to decreasing. So here you should have a local maximum. Whereas at 3, even though it is a critical point, the function is decreasing to the left and decreasing to the right. So 3 is neither local max or local min. So that's how you find local max or min. Or you can do the second derivative test, where here you find a critical point, and then you look at what's the second derivative at the critical point. And this can give you some information if it's non-zero. For example, if this happens to be greater than 0, that tells you you have concave up, so you're opening up like a smiley face, so you have a local minimum. If it's less than 0, then you have a concave down situation. You make a frowny face, and then you have a local maximum. But I mean, here it can fail. It might be 0, V double prime might be 0. In that case, you have to go back to the first derivative test. So that's what you want to do if you're asked to find local max or min. For global max or min, the technique is very different. Here what you do is you look at the critical point, and for endpoints, depending on whether the endpoint is included or not, or you have plus or minus infinity, maybe you have to take the limit. And for global max and min, remember the question is always phrased like this. You have some f of x, some function, and it's on some interval. Maybe it's like 1 to infinity, and you are trying to find global max and minimum. So here, you don't make any sign chart. If you find yourself making a sign chart when it's a global max and min, you're probably doing it wrong. So make sure you use the right techniques. Here the key thing is you look at these points, and you should just plug them into the function and compare function values or limit. I have a video in which I go through global max and min very carefully. So if you're interested, make sure you check it out. Anyway, going back to the question, finally, you want to figure out where v of t has this local maximum. First, we gotta find the critical point. So this is where v prime is 0 or undefined. Can this be undefined? Well, for it to be undefined, you want to be dividing by 0. But e to the bt, this is always positive. So you're never dividing by 0, so this is always defined. So you don't have to worry about being undefined. But can v prime of t be 0? Surely, the top can be 0. Either this can happen by t being 0 here, or bt minus 2 can be 0. And when is bt minus 2 0? Well, that's when t is 2 divided by b, right? You just set this to be 0, find t. And now we're looking for local maximum here. So all you have to do is make the sign chart. So I wrote down the sign chart to make sure you write v prime of t, and you're looking at 0 and 2 over b. So how do we figure out the correct signs? Well, to the left of 0. So to the left of 0 here, you're plugging in some negative number. When I plug in a negative number, t is going to be negative. bt minus 2, well, b is positive. So when I multiply that by a negative t minus 2, that's negative. E to the bt, that's always positive. And make sure you see this negative sign. So let's start with this negative sign. So you have minus. And here you have negative times negative over positive. Make sure you write this out so you get the points. So negative times negative divided by positive. And this entire thing is, of course, negative here. So this is negative. What about to the right of 0? When I go a little more to the right of 0, what happens? So when t is 0, this thing is 0, and this thing is negative, right? And when I change t a little more, maybe t is like 0.001, something less than 2 over b. So when I move a little more to the right, then this t now becomes positive. bt minus 2, you only move t a tiny bit. So this thing is still going to stay very close to negative 2. So this thing is still negative. So what we get now is you have this negative sign up front. And here, now we have positive and times still negative divided by positive. So this thing is now positive here. What about to the right of 2 over b? Well, when I plug in something larger than 2 over b, then, first of all, t is positive because 2 over b is positive. bt minus 2, well, bt minus 2 was 0 here at 2 over b. But now you're plugging in something larger than 2 over b. So when I put something larger than 2 over b here, since you're multiplying t by b, which is positive, as t increases, this entire thing is going to go up. This entire thing is at 0 when t is 2 over b. So when I plug in something larger than 2 over b, now this thing becomes positive, right? So what we get now is we get negative times positive over positive. So this thing is negative. So what do we know about 2 over b? Well, the function is going from increasing to decreasing. So 2 over b we see here is in fact local max. And that's exactly what we wanted to show. Let's do the final part really quickly. Lin knows that it took 8 seconds to inflate the balloon, and at time 8 seconds, the volume was 1.5 cubic feet. So we know V of 8 was 1.5, and if you remember the formula for V of t, when I plug in t equals to 8 here, what we get is 64a divided by e to the 8b. So this is the expression you get. But we want to find a and b, but we have two variables. How can you find a and b here? And now here's the key observation. It's that it took 8 seconds to inflate the balloon, so local max is happening at 8. Because if you go back up to this picture, you inflate the balloon until 8 seconds, and then the balloon starts deflating after that. So you know the local maximum is happening at 8 seconds, and we know from the previous part, I guess I forgot to write it, it should be 2 over b here. We know the local maximum is happening at 2 over b, so we know 8 is 2 over b. So I'm running out of time, so I'll now leave it up to you, but you can find b using this equation. You'll see that b is 1/4, and now you can plug in 1/4 into b, and then you can use that to find a, because a is now the only variable, and you'll see that a is 1.5 e squared over 64.